In this video, we're going to begin our detailed look at nucleophilic acyl substitution of carboxylic acid derivatives, focusing first on acid halides and then anhydrides. So as we begin with acid halides, keep in mind that the acid halides are the most reactive, which means acid halides can be converted to anhydrides, they can be converted to esters, and they can be converted to amides. So for example, if we have an acid chloride and we react it with a carboxylic acid, we can make an anhydride. If we have an acid chloride and we react it with an alcohol, we can make an ester. An acid chloride reacting with an amine gives us an amide. And like all carboxylic acid derivatives, reaction with water will give us a carboxylic acid. Notice, as we're going from the acid chloride plus the carboxylic acid to give the anhydride, what's the byproduct? And that's going to be the byproduct in each of these cases. We are making HCl. So this is going to have an impact on some of the details of the reactions. So just keep that in mind. Now let's consider the details of one reaction of acid chlorides, and that would be the reaction with an alcohol to give an ester plus HCl as a byproduct. Starting out with our acid chloride, this can react with the alcohol. The alcohol is the nucleophile. It shares its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen, giving us this species. Now, most likely, this is going to react with a molecule of methanol, can grab off this proton, putting these electrons onto the oxygen to give us this neutral species. And then that gives us some protonated alcohol, so that the O- can grab off a proton from here, giving us this neutral part. What happens next? Some base, and once again it's probably the solvent, and so methanol can grab off a proton from here, putting these electrons back in here to reform the double bond, and if it kicks out chlorine as the leaving group, then our resulting product, we have our methyl group connected to the carbonyl, still connected to the OCH3, so we make an ester. What if this happened a little bit differently? So if the methanol grabbed off this proton, these electrons came back in here, kicked out this. Well, that would result in CH3, C, double bond O, Cl, plus CH3O-. In the last video, we discussed the relative reactivity of the different carboxylic acid derivatives. And we know that we can convert an acid chloride to an ester, but we cannot convert an ester to an acid chloride by nucleophilic acyl substitution. And the reason is right here. What we're looking at is a competition between Cl- as a leaving group and CH3O- as a leaving group. When we think about leaving group ability, so Cl- versus CH3O-, we can compare leaving group ability by thinking of these as bases, and therefore we want to compare the acids, HCl versus methanol. Methanol has a pKa of around 16. HCl has a pKa of, I don't know, -5 or something like that. So this is definitely a strong acid, which means this is a very, very weak base. This one is a stronger base. As we compare a weaker base versus a stronger base, we know that this is more stable. This is going to be the better leaving group. So in this competition, when these electrons come back in and either Cl- gets kicked out or OCH3- gets kicked out, it's going to be the Cl- because this is a much more stable leaving group than this is. So if we were thinking about going from an ester to an acid chloride, we would come to this same tetrahedral intermediate, but we're not going to kick this out to form the acid chloride. We're always going to kick out the chloride to form the ester. So we can always think about the dissociation of the tetrahedral intermediate as a competition between leaving groups. Next, let's consider nucleophilic acyl substitution reactions of anhydrides. So here we have an anhydride, so we know that an anhydride can be converted to an ester and to an amide, but it doesn't go in the other direction. So if we have our anhydride and we react it with an alcohol, we can make an ester. If it reacts with an amine, we can make an amide. And if it reacts with water, we can make a carboxylic acid. In these reactions, our byproduct is acetic acid. So once again, we have an acidic byproduct, which sometimes is going to require a little bit of attention. But we'll talk about those details in class as we work through some problems. Now, what if we want to consider converting our anhydride into an acid chloride, right? So we want to try to go the other direction. Once again, think about this competition. If we were able to add chloride, if this added here, then we're going to get to an intermediate that looks like this. Now, as these electrons collapse back in, it's a competition between this as a leaving group or this as a leaving group, and chlorine is the better leaving group. So we would just get back our anhydride. We cannot convert the anhydride to the acid chloride. Here's an example of an anhydride reacting with an alcohol to form an ester plus carboxylic acid. And if we think about it as if it was under neutral conditions, then our alcohol would add here, push these electrons up onto the oxygen, and then we get this not so good species where we have a positive charge and a negative charge on oxygen in the same species. That's not really common, but let's just go with it for a minute and imagine we're going to have some proton transfers so that we get to both of these neutral. And then alcohol, for example, can act as a base, grab off this proton, push these electrons back in, kicking out this guy as the leaving group to give us the ester plus the carboxylate. So because this intermediate, it just looks weird, right? Well, actually, this reaction is typically not carried out under neutral conditions, but it might be carried out under slightly acidic conditions. So this oxygen would grab a proton, and now we have a protonated anhydride, which makes this carbon more electrophilic so that our nucleophile can add, pushing these electrons up onto the oxygen, and now we have this intermediate where we have a positive charge and no charge. So not that positive negative thing. Still, we're going to have alcohol can grab off a proton and we get this tetrahedral intermediate, and then the tetrahedral intermediate can break down into the ester and the carboxylate. So many of these reactions will be carried out either acid catalyzed or under basic conditions, for example. And it's just important to be aware of the different species that are going to exist. But still keep in mind the big picture. The nucleophile adds, we get some form of a tetrahedral intermediate, and then the tetrahedral intermediate dissociates to give us our new carboxylic acid derivative.